All right, so the homework, it was pretty low score in homework, but I'm not sure there's that much impact on final grades. But the problems, I guess, let's see, this A and E, everyone got that well, and then so equation 2 is that thing. So basically, I think a lot of people got that right.
Which part of
Oh, wait.
were you looking for specifically?
Actually, for this thing, one group got it right, and one group kind of got close for B, right? So what I'm looking for is like you had to do first, you had to solve this integral for the condition of with the fixed value of nu, which is 1/2. So B, so it goes B is the A is 1/2. So A is 1/2 on this. Let's see. A is 2. So nu is 1/df. So A is 2. So 2 minus 1 gives you 1. In the one case, in the other case, it's 1/2. So 1. So then this term just drops out, and just integral of exponential is exponential. And then you put in the limits of it, B, which is u, which in the where nu is 1/2, u is just q squared or g squared. So you plug that in, then you get those two limits, you get e to the minus q squared or g squared, and then it's like +1, I think, because I guess it's minus 1. And the other one you have to do by integration by parts to get it, if it's t to the 1, which one group did. So I gave them like 3 points or something, but then one group two groups did that. So first thing is to solve those two integrals, and then plug in the other values, knowing that this u is q squared or g squared, and then do algebra. I think it's just do algebra on it, and then you'll get this, the Debye function thing. You'll end up getting that, this guy. All right, so except capital Q is small q. No, capital Q is q squared is u. Right, so I mean, there's a change in nomenclature in it. So anyway, so that was 2 groups did it out of 11. So it is, if you didn't do it, it's not unusual, you know. I think at varying degrees of points off at maximum 11, 10 out of 20, you know, if you didn't, I don't know. So a lot of people got 10 minus 10, and they ended up getting a 70 something on the thing, because this problem, I don't think it'll have any consequence in the long run on the grade for the class, but but some people have like smoked through this thing, all the questions, like one group, so it is possible to do, you know. But so what was it on B? Is that the answer?
Yeah.
All right. I mean, I mean, some people.
And then I couldn't find the slide number to get to the competition.
Oh, okay. Did you get points? So you did all that with it? Okay.
I got it.
Okay.
I just think it's the proper form.
Yeah. All right. Yeah. Well, that actually the main point of it is that equation, you know. So it's kind of like, but anyway, it's okay. If you tried to do it, that's pretty good. The real theme, that equation is important in polymers scattering, you know. But basically, the idea of like, so you have a known function, you know, the idea of like you have a function that looks like it's impenetrable, like there's no possibility of understanding it. Then you have a function that you know is the right function, and there's some condition. That process is really important to know. You know what I mean? Because then you can at least get comfortable with something you have no idea where it came from. But you have like a marginal idea. You can, or they give a really obtuse derivation, so you can follow through it, but you never really have a warm, fuzzy feeling. So it's something that you need to do, you know, when you're looking at this kind of thing. So then another thing you need to do is to take it to limits where you know the answers, like this thing. So I did that in class for this. I did that in class for the Debye function. somewhere here. Lost from my thing here. I like go up the stairs before I come into class, so I check my heart rate on the way in. That's why this thing always beeps, you know. So if you hear it beep, you know I didn't die from high heart rate or something. Anyway, somewhere in here, I do that to extrapolate the Debye function. I guess right here, right? So you find out that it's 1 over q to the minus 2 at high q, so it's 2-dimensional, q to the minus df. At low q, you can extrapolate Gurnier's law from it. Right? So I asked you to do the same thing, but for this like monster equation, not in the, so one group did it in the limit that you just did for b, which isn't the intent. The intent was for this equation, like to show that you get, in this case, you would get 1 over df instead of 1 over 2. Right, so one group did that. But one group kind of got close. And
Yeah, I was confused on which one I should have used. So I was working on that one.
yeah,
Like 3 different, like, or experiment.
yeah, it's not easy to do. You know, it's possible to do it. One group did it.
What was the correlation you were looking for?
So you should get it, high Q would go 1 over, so it would just be a power law of 1 over df. Like that's just a fractal. So you have the fractal,
High.
yeah, the high Q and the low Q, everything should go to Gurnier's law at low Q. Every scattering equation should go to Gurnier's law at low Q.
So
Right,
the high
so-
one did not correlate with it.
No, the high, they work, you can get it from it.
Oh, you can't.
Yeah, you can. Yeah, the thing you can't, I wasn't able to exactly get was the next question, thing about getting this equation. But this thing you can get. It's just kind of tedious to get it. So, because I mean, the exponential, if Q gets large, it doesn't matter what the argument is, this thing still goes to 0, right? E to the minus infinity 0. And then if Q goes small, this thing still goes to 0, so that thing is still 1. So all the new things disappear. And then so I think you can kind of figure it out that way. You know, the exponentials disappear, and then so everything kind of simplifies, and you can get power law at high Q, and you can use it if you do those on it. So it's possible to do that. I don't want to. I guess I could write out the answers if you guys want, but doing it in class would take too long, I think. And it's kind of like pointless, because the point is to show you like how you deal with something. There's this function, it's absolutely indecipherable, right? So and maybe it's marginally decipherable if you go back to the Benoit paper from 55, but basically what you want to see is that it behaves the way it should behave. You know, so you want to say like, how should it behave in extrapolated limits? Then I know an answer for this, which is when it's df2. So see if I can get that answer too. Now, if you have those 3 things and you kind of like, okay, at least it behaves the way it should behave. It's not going to be a crazy function. Right, so that's the point. And the point is, this is an example of that kind of thing. So you run into this in everything you do. So you shouldn't just so blindly, and the other thing about weird functions is that you have the data and you're going to fit it to some function. And look at the data and like how many parameters can you actually get out of the data, and how many parameters is a function given you, right? So I mean, it can't be that you get more parameters than what are in the data. You have to be able to look at if it's a straight line, there's 2 numbers you can get, and that's it. So if someone gives you a straight line and they start saying, in dielectric spectroscopy, this is pretty common, they'll fit it with these complicated functions. So you get the capacitance, the resistance, the impedance. So you get like 8 numbers out of a fit. Then they'll go back and it's like if you paint metal, and you want to talk about corrosion of it, and you do dielectric impedance on it to get the functions for the kind of electric circuit of the paint on the metal. This is where I've seen it most commonly. We used to have a couple of guys that were the top people in paint, like kind of in the world here for a while. And so there was a lot of this dielectric spectroscopy. They'd come into their PhD dissertation, they'd show a plot, it's like a straight line, okay? So then when they come out, they'd have like 8 numbers that they got out of a straight line. It's like, if you know nothing about dielectric spectroscopy, you can tell them right off that 2 of those numbers might mean something. Actually, even the two that might mean something are corrupted by the other ones because you force the fit. So none of the thing that they did out of it is worth anything. Right. And you can say that pretty much with confidence, even if you know nothing about what they're talking about. Right. So it's pretty useful to be able to do that. I mean, you can ask them like, there's two numbers, where did the others come from? And they'll be like, blah, 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 it's a function, it has to work that way. And it's like, well, that's not true, you know, it can't possibly be true. So
So that integral at I and both u will always go to zero. That gamma function.
yeah,
Always will be at the extremes will be equal to zero. So then. What happens to the?
this is one, right? E to the zero, if this is high, it's minus infinity, so this goes to zero. Yeah, that goes to zero at any limit. Yeah. Well, that would give you zero for the whole thing.
Yeah, so I'm kind of looking at the integral, like the solve integral.
Uh-huh.
Even at low and high q, both integrals at one, like u equals to 1 and 2, which is.
At low q, you expand the thing because then the argument's small, so you can expand it to 1 minus t plus t squared over 2 minus t cubed over 6 minus t over 4, whatever.
Okay.
4 factorial. So, and you keep as many terms as you need to get Guiney's law, because Guiney's law already is an expansion, so it'll have extra terms too.
And that's because there's 4 parameters, right, that you can get from it, the 4 that comes from.
No, that's a separate thing. This is just saying, you know what the limit should be? It should be 1 over q to the minus df. And it should be Guiney's law. So you know those two limits. So what do you know about this function? So you have the data, that's a separate thing. The data has 4 numbers in it. That's what you can get. But the other end of it is you have this function. You know that the function has to revert to this function, known function that you're kind of comfortable with. And also, you know, that the limits of it, like the limit at the high parameter and the limit at the low parameter. Low parameter always has to be Guiney's law. High parameter, it has to be this minus fractal thing. So, and if it's a different field, I mean, there'd be different limits. So you'd have to kind of know what the limits would be. You know, like I think at high frequency, let's see, at low and high frequency for dielectric, I think at low frequency, you get the resistance, and at high frequency, you get the impedance or something. So, or the capacitance. So basically, the two limits of it will give you the capacitance equation of resistance, like Ohm's law at the other end. So basically, it's the same kind of thing, like, you know, kind of facts about it at the limits. And in between, you're trying to describe the depends on frequency. So you get the circuit thing. So anyway, so it's applicable to a lot of, so that's an example, another example of like a complicated thing we might know nothing about, you know, that you can still critique. Anyway, so that's C. And then D's dice here, so basically he gives you the answer, like he's got all these parameters, then because he only can get 4, he's going to reduce the 5 that he has by 2. So he ends up with 3 parameters. So he could possibly get 4 parameters and he's fitting it with 3. So that's a reasonable fit. And in other words, if you can fit the curve with 1 parameter and it has 4 parameters in it, that means your model is pretty good. If you can fit it with 2 and it has 4 parameters, then it's pretty good. 3 is good, and 4 is like, well, it's kind of like fitting it to a polynomial at that point. Like you fit it with a polynomial or your function, right? Neither one would work. So like a polynomial with 4 terms in it, up to the cubic term, right? So anyway, so he reduces it down to 3, so that's good. And then the idea is like, what does that equation go to? If you say it goes to those 3, and then does it reduce? Can you reduce it to the RPA equation, which is 1 over? It's going to be like 1 over this S. Let's see, where's this equation? So this S110 would be like the polymer 1. I get, or the Bobo ball things, and 220 would be the polymer ones if they were isolated, like in dilute conditioning. Right, so the total mixture of them should be 1 over the concentration times S110, and then 1 over the concentration times, or the contrast times S220. And then the concentration, I think, comes in the top. So so basically the two dilute conditions give you the total condition. And then it should be minus 2 chi at the other side of it. So that would be the RPA thing, kind of like, well, it looks something like this, but these S11s aren't. So this involves a 1 over. This S11 involves 1 over the dilute ones. That's the idea, was like hammer that through. And I kind of expected you to try to do it and then kind of get halfway and give up. So anyways, yeah. Right. That's what I got to too. That's exactly where I got. And then I got to that if you, where I got to was that if you said that there, whatever the equilibrium point, or the what is it? He gives it here someplace. I showed it to you before, but it's a difference between the 2 chi and the 1 over S33 has to equal 0. Or it has, yeah, it has to equal 0 to be. And then if you do that, you get the RPA, but without the chi parameter. So yeah, wherever you got is where I got it, I think. So that was good. I think only, like, maybe you were the only one that did it. So that's all right. It's again, it's like, it's a fact, it's a thing about, you have this really messy equation. So how do you have any faith in that? You know, like, how are you going to believe that? You can go back to the Benoit paper, you can see that it's pretty clear how he derived it. But if you don't have access to that, and I still don't have the book, the Humuda book chapter. I requested it from the library, but they didn't come up with it. So anyway, you can look at the derivation and see if you believe it, or you can say, does it work out under conditions where I know the answer? Like, you know, it should go to the RPA in certain conditions. So anyway, it's a little bit of an exercise in complex equations, which, I don't know, I think it's a good thing, something that you should be taught. But it seems to be left out for the most part. I think it's something you pick up it's something you somehow pick up, you know. But anyway, it should be a main course thing in the teaching of engineering, because you're dealing with a lot of equations in engineering, and like a lot of them, you're not going to be able to go back and find the root, or even if you do, like these equations of state for petroleum, you know, for phase separation of like different alkanes and things. I mean, there's a lot of like foo-foo dust in it, like just make up this and that. So how do you believe it? I mean, it works in practice, so empirically, like you don't need to understand how the steering works in your car. Like nowadays, a lot of the steering is done electronically, you know. So there's an electric motor that turns the wheels, and there's like a wire that goes to a computer. You turn the wheel and you feel like you're actually turning the wheel, but you aren't. You know, like, so it's that kind of, yeah, it works, so I believe it, but it would be nice to know, like, to have a little bit better way to deal with these equations. That's all. I mean, and this is kind of how you do it. So you have to, it takes a little bit of thinking. It's a good thing to get used to doing, I think. Like, don't walk up and say, like, there's no possibility of understanding this, blah, 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 and then it's a blur and it's gone. Like, that's not exactly the right answer. You know, so you have to be able to say, like, so he's challenging you to test, to say, like, no, this is bogus. Like say, if you go in to get a PhD or something, you have to review papers. People will send this paper to you, and you have to say, like, is this right or not? And going through the derivation, maybe it looks okay. Then you have to be able to kind of tell them, like, that it isn't right for whatever reason, you know. So it comes to a point where you need to decide, and that's kind of how you decide, I think. Anyway. So everyone did well on EA and E things, and that's about it for that. Need other things about that. So I'll get rid of that guy. Then I wanted to go through somewhere like just finish off the scattering thing and then maybe get to, next thing I want to do is hydrodynamic radius and like dynamic light scattering and that kind of stuff. So, and intrinsic viscosity things. So basically, today I'm like a little bit on scattering things, and then we'll be done with that. I do scattering, so that's like I'm pretty fond of it. You know, so, but it also in polymers it tends to show up. So because of disordered materials. So this idea, all right, so a lot of the scattering equations have some problems, you know, that people use. So we have like this equation, which Debye derived, and it's analytic. It comes from the this Gaussian walk idea, and just it's pretty clear where if you read the papers, it's pretty clear where this came from, right? So this is straightforward. You can take this as a fact, and it matches the data also for Gaussian chains if you're at the theta condition. So then Ornstein-Zernike equation is this thing. So if you looked at when we did the Zim equation, so this is if you take 1 over Guenier's law, then do the exponential expansion of e to the plus q squared rg squared, you get 1 plus q squared rg squared over 3. So this is a Zim equation. That's just 1 over Guenier's law, basically, is where he got it from. And then he parks in front of it this osmotic pressure, osmotic compressibility term from the osmotic pressure thing we did, whatever that is. Anyways, wherever I had the slide for that, it's gone now. Anyway, so that's the Zim equation. So if you take that equation and you flip this back over, then you end up with this equation, okay, which is 1 like some number, the contrast over 1 plus q squared something squared. Right, so that's called the Ornstein-Zernike equation. So Zernike won the Nobel Prize not for this, not for the other things that he did, which was like the Ornstein-Zernike equation, which I'll talk about in like a little bit later for scattering, about correlations. Right, he won the Nobel Prize for a confocal microscope. So he invented the microscope, kind of a way to image in 3D space, like in the 50s, something like that. Right, but he's not really known for that. He's known for this Ornstein-Zernike correlation equation. And in a footnote to one of the papers on that, he gives this scattering function. And he says this just happens to fit things that have like fractal dimension 2. And it does, he says you shouldn't take it analytically to mean anything. There's just this equation. So, but all right, so it kind of, but you can go back and say like Zim equation, flip it over and you get that. And Zim was talking about polymers. So Ornstein wasn't talking about polymers. He was talking about quote unquote disordered systems. So something like, so he didn't call it race gyration because he wasn't talking about anything. He was talking about like, you have a mess, you stick it in the beam, you get a scattering from it, it has a 2 IQ minus 2, and then you get this function could fit it. That's more or less what they said. No, so yeah.
So they use zeta in there because they treat it as like polymer coils. Is that like something else?
That's called the correlation length. So, and that also doesn't have a definition. There is a correlation length that means something, but this one doesn't mean anything. It just means it's some size parameter that comes out of this function. So it doesn't connect to anything. Nonetheless, then since this is a simpler function, and you can take derivatives of it, and you can do a Fourier transform of it. So it's like this function, you can't do a Fourier transform, so you can't get a correlation function from it. But this guy, you can easily do a Fourier transform of it and get this correlation function. It's kind of a simple function, right? So people kind of gravitated to this function. And then eventually this became like the replacement for this function. Just, you know, because people like that it was simple math. Like this thing's complicated, that thing's simple, this must be better. Right. But it isn't better because it doesn't match the actual numbers, right? So anyway, so this is a problem. The other problem is, so if you have the correlation function for a so if you have a correlation function for a surface, you have the surface to volume times R. So you have the correlation function. This is called a porod. function. Right, and if you, before you transform that, you get the surface to volume times 1 over q to the 4, minus 4, q to the 4. Right, so you get this steep slope. Polymer is going to be weak slope, log I, log q. Minus 2 is a polymer, minus 4 means a surface, right? But this thing comes from this idea that you have an area, a material, and then there's a porous region here, and you have that vector r that can fit within the region, and then r, so r times s gives kind of the volume of that region, and then there's the total volume of the system. If you're in this part of the system, so you have correlation between these two, so you have constructive interference in those 2 points. There's always a middle point that kills off the constructive interference. So basically the only scattering you get is from that surface area. So the surface to volume ratio gives you this. This will give you that correlation function. If you think about the probability of a rod falling into that volume, right, over versus the total volume, then you end up with so it's like the ratio S times R over volume gives you the probability. So 100% probability that one end is in the particle, and then minus that probability that it's in that interface part gives you the correlation function for a surface. Anyway, this thing has like a direction, right? Because it's a surface. So that means that the correlation function can have like plus and minus can have opposite features. Like you're only talking about plus away from the surface when you're doing this. Right, so generally correlation functions so this is kind of an ordered system because of that. If it's a disordered system, like with Beaucage's law, if we look at this smeared out particle and it ends up being just a Gaussian function, then you end up with a correlation function that's like r squared. Exponential minus r squared depends on r squared, so it doesn't have a linear term, like 1 minus r squared. Doesn't have an R term. So Beaucage's function doesn't give you a surface. There's no surface to it. So that the linear. So anyway, this function, you'll notice, has this plus minus thing. Like it isn't symmetric about 0, meaning that it's got direction to it. So if you have a random system, so like Beaucage's law, like a randomly oriented system, then you can't get a function that has direction to it, which this one does. Oh, sorry, yeah. Sorry about that. So this guy has directions. That means that this isn't a valid correlation function. Like you can't have a correlation function. It can only have r squared, r to the 4, r to the 6 in it. It can't have r. So this thing has a problem. Okay, so it's basically, yes, you can transform it and get that function, but this isn't a valid function for the kind of system he's talking about, which is a random, like a polymer chain, like the Debye equation, which depends always on like q squared in it. Right. So or 1 over r squared, right? So anyway, so there's a problem with this thing. So anyway, so nonetheless, this thing is, you'll see like all over the place. So if you want to look at it, you can do this extrapolation business. You can say like high Q limit, this thing gives you, this equation gives you at high Q, Q is much larger than 1, so it just gives you that thing. So you get, yeah, you get -2 power law. And then with the Debye, you get this thing -2 power law. If you extrapolate this to a high Q, you do low Q, you get kind of Beaucage's law here. You get exactly Beaucage's law here. You get this kind of Beaucage's law. But if you equate this correlation length with RG, you get that relationship at low Q. You get that relationship at high Q. So it's not matching this function. They don't match, right? So it isn't describing the same thing as that. So it means this one's wrong. And also the correlation function itself is wrong. So basically, you'll see this Ornstein-Zernike all over the place, but it's not a valid function. So that's step 1. And then other functions that you'll see a lot in polymers and soft matter stuff is like these functions for scattering. Okay, so first, if you get rid of the R here, so if you had the Ornstein-Zernike, and then you get rid of the R, then you also have a function that's not symmetric about 0. So it's not a random orientation structure. And then if you transform that, you get this function, which gives you Porod's law at high Q. So when Q is larger than 1, you get Q to the -4, but you get some weird thing, something like Beaucage's law, but with the power 4 in it instead of 2. at the low Q. So this can kind of fit data that's something like polydispersed spheres, but it's not right because the correlation function's wrong, and this is kind of a bogus thing, right? So, but this nonetheless, these are the tenet functions in scattering, you know. So then you run into this business, like if you have a colloid, then you get like in my cell, it'll give rise to a peak in the scattering. So you need some function that'll give rise to a peak. So this Tubman-Stray group came up with this function, which is kind of like take the Ornstein-Zernicke and then just add on the bi to it, and then say that the C2 is negative and C3 is positive, then you can get a peak in the scattering. And this function also has a Fourier transform, which is this thing. Right, so first off, they took this and that, put them together, got this, then realized that you could get a Fourier transform of it, got this. So this thing isn't derived or anything. It's just like something, right? So anyway, so this is kind of how things have gone. You know, you start with something bad, you make it worse, and then you can just pile on. So finally you get to the Sinha function, which is for an arbitrary fractal, which also has the sign problem. It's not symmetric about zero for a random system. This is supposed to describe things like silica powder, silica aggregates, things like that, and also polymers. So sometimes people use this for polymers. And then it looks a little bit like the Ornstein-Zernicke. It's got that term in it, but it's to the fractal dimension, so you can have different fractal dimensions in it. Right. So you have to be kind of careful. If you go back to like this kind of limits and then have a function that you know, you can show that these things aren't true. But it doesn't help much because they've been published and people just cite the paper and it just goes through. So basically you get these functions a lot in scattering, and basically once you go that route, like this number doesn't mean anything. This correlation length is just some fitting parameter. You might as well do a polynomial fit. Right? It's actually you're better off with a polynomial fit because you could conceptually relate the polynomial parameters back to this function to figure out what they mean, you know. But and you wouldn't be tempted to say that this correlation length is a radius of gyration. So that's just like words that are wise for this, kind of what you'll see in the papers. I tend to not, if I find a paper that's got this function in it, I don't tend to not give it to you because I don't believe it, you know. But so there are quite a few. I mean, probably this function is probably used more than the Debye function. Anyway, that said, that's probably not no use to you. But then I already mentioned like, so in scattering, you're gonna end up with this kind of business. Like when you talk about polymers mixing, then you're gonna measure the interaction parameter with the RPA equation. If you take the intensity divided by concentration, then as you add concentration, this reduced intensity reduced by concentration drops, because if you take a single chain, you can get the scattering function, which is gonna, well, I've done it for a fractal thing, it has 4, but this would be 1 out here for a polymer. But anyway, so if you have that thing, you get the scattering function. That's the total size, that's the small scale size, and this would be the surface area if it had a surface area. Right. So as you add concentration, you lose at some point at the overlap concentration, you lose the ability to see the object, right? Because they're overlapped. So you can still see at a small scale the same thing. So that I by intensity by concentration is the same at the high end, but this low end starting to get swamped out because you can't see the fibers anymore. So what you see is actually a real correlation length, the size of the hole, like the size of the hole in the system. What's the spacing of the things? So you can see up to that point. Beyond that, at lower magnifications, it starts to just look like a sheet, like you just see uniform. Okay, so as the concentration increases, that correlation length, that hole size gets smaller. So this thing moves over to the right and 1 over size. Eventually you get to just the things. That's it. You can't get any more information there. So because they're packed. In other words, these are 3D objects, they would pack solidly at that point. So you can get the size of those objects, but that's it. Right. So that's kind of what happens. Right. So this assumes that as these things are being packed together, they don't form like a crystal. Or if you want to think about it in terms of like fabric, like you're making a fleece, like this kind of material, right? And then in the other case, the things are ordered. So you're making like this kind of material. But far away, the two things look the same. Like from far away, they're identical. So for both of them, you're going to get a plateau over here. And the rate of drop of this thing is going to depend on like how dense the fabric is woven, or how dense the fibers are spun, or whatever you call it when you make a non-woven, right? So basically, this end is going to be how well they can pack, and that's got to do with this interaction parameter, like the interaction between the things, right? So if you get above that, then in this case, you're going to see a peak to the correlations of the thing. In this case, you just see nothing. Right, so those are like the two options. This is called a mean field because there is an interaction. The interaction, the chi-parameter is driving this thing down, right? And this is called specific interactions because of specific ordering of the thing going on. Right, so you can see both of those. I mean, if you have polyelectrolytes, you can get this kind of behavior in polymers, and then if you have uncharged particles, you can get that kind of behavior in particles. But generally, this is going to be like colloidal silica, like silica spheres that are perfect spheres that are like charged and opposing each other. That would be the model system here. The model system here is a polymer for mean field. Right, so you'll see this like a lot in the literature. Like we'll talk about, oh, it's mean field behavior that we're looking at. That means they're not looking at any specific interaction of the things. Right, so and if this is, so here you can see the same effect if you change the temperature. So if you change so this is changing the concentration, so the packing, and this is changing the interaction. So like you change the temperature, these are series at different temperatures. You see the behavior because chi is 1/t, so you'd see that behavior. Same behavior with temperature. You change the screen length, you change the correlation length when you do that. So sometimes you'll see well, it's called an Ornstein-Zernicke plot. So you'll see a linearization of those curves using this equation. So you'll plot like 1/I versus Q squared, and that will linearize this equation. And then the limit of that at low Q will give you this chi parameter more or less. So there is like a 1/I versus Q squared plot that looks a lot like the Zim plot, whatever that is. Zim plot's here. That's a Zim plot. So this is R here is a Rayleigh ratio. So that's 1/I. So it's intensity divided by concentration. So it's concentration by intensity. And this is sine squared. Q is sine squared theta by 2. So Q is sine theta by 2. So Q squared is sine squared. So this is Q squared. Right, so that's like a Ornstein-Zernicke plot, except that they add in the concentration term from this Flory osmotic pressure thing, osmotic compressibility. And then you get the Zim plot would be like extrapolate both angle and concentration. And when you get to zero concentration, zero angle, you get the molecular weight. And then from the slope of the constant Q, you'll get the chi parameter in this term. And from the slope of the constant concentration, you get the rate of gyration by 3, rate of gyration squared by 3. So this thing they'll use in a GPC, but in a GPC, so you put the polymer solution into a column and it's going to fractionate it. So you get just like extremely dilute fractions coming out the end, right? So your concentration is 0 in the GPC, right? So it'll have a light scattering detector that detects at like 3 angles. You're already at 0 concentration, so you're already at the black line for each fraction that's going through. And with the 3 angles, it can draw a straight line. It can get the molecular weight of that fraction, absolute molecular weight, right? And because it's a narrow fraction, the weight average is the same as the number average, same as the every average. And then you can also get the rate of gyration of it. And if you know the rate of gyration and the molecular weight, you can kind of figure out how branched it is. right? Because you can kind of say, well, if it was in a good solvent, you could predict from the molecular weight, radius gyration, but it's monodispersed, right? And then, but if it's branched, it would be a different number. So so from using a light scattering detector and a GPC, you can get a lot more information. You can get information about each fraction that's coming off, like the structure of it. You get the absolute molecular weight, so you don't have to have a standard. And you also get the this idea about what the thing is from it, so it's kind of a useful detector to have. It's more expensive than an index detector, just give you the concentration. So anyway, so it's that business. And then, all right, so the other thing is this is just a picture of a GPC. If you went to, which one of you went to the tour of Lyondell, they have a whole, because they make polyethylene and it has random branching in it, right? So they have to figure out the branching all the time. So they have a kind of a half of a floor. Yeah,
It's gel condition.
yeah, or SEC, so yeah, same thing, yeah. So they're out in Mason, whatever, it's like Mason, I guess, almost between Montgomery and Mason, near 275. So they have like half a floor of a building just GPCs. If you go to their research place in Frankfurt, they have like 2 buildings full of GPC machines like this, and they're just running their resins through all the time. So it's like a lot of it here is like troubleshooting. So they'll take their resin, so they know what the structure is when they make it. Like they try to have controlled catalysts, so they get controlled branching. And they send it out, someone extrudes it, the extruder jams up, which means a train load of plastic is going to be tossed, literally, right? So then the guy has to go out and figure out, troubleshoot it, figure out what's going on. So they get the samples of stuff in the extruder, bring it back and say, like, is it the same? Then like what happened to it in the extruder? Like your extruder temperature is too high. You can have hydrogen abstraction and cause branching in the process of extruding it. Or the resonance time in an injection mold could degrade the polymer so that it branches more and you get something different than what you put in. In fact, it always is different than what you put in. So everything is kind of like just a shot in the dark. Like you start with a thing and you have a pretty controlled structure, and then it's going to go through a pelletization process, and it's going to be shipped somewhere, then it's going to go into another extruder. Maybe they're going to blend a blending extruder. Like it could go up to Poly 1 in Cleveland, and they'll mix it with pigments and things, make a color concentrate. Then like that'll be shipped somewhere else. So it's going to go through a lot of extruders before you get to your plastic cup, or whatever widget that you're making. So it's basically, that's a lot of what they're doing is troubleshooting by GPC and a couple other methods to figure out like what's going on. So anyway, so you'll see a lot of these machines. There's one up in chemistry that we could look at if you want. Neil Ayers' lab has actually they have 3 of these. So no, Neil Ayers, Ayers. Yeah, he's in chemistry. So yeah, so this is the idea. Like this is polymers. This is kind of like colloidal stuff with a specific interactions, like colloidal silica. So this is not silica filler or silica whatever, like the absorbent things you get with the drying agents you get with whatever. They'll be like packed in. Will be a little packet of silica. Yeah, desiccant. Yeah, this is something different. This is used for what's colloidal silica used for? They use it to treat film to keep it from sticking together. You can biomedical, they use it for something, but you can attach things to the surface and make like delivery things with it. So there's a lot of research with colloidal silica. Anyway, it tends to, you can see it's crystallized into hexagonal. This is a hexagonal ring, I guess. It tends to form a hexagonal crystal, like either FCC or HCP, right? So anyway, you'll get from one of these spheres, okay, then this is the function, the form factor for a sphere. So the form factor for a sphere has peaks in it. It's this sign expression. That's the scattering factor, would be our Debye equation for the polymer coil. This is what it is for a sphere. So you can do that if you want. You can take this equation, you can plug in the expansions for cosine and sine at small q, and you get Guignet's law out of it. If you do this for high q, you get So how do you get this? The average of sine is 0. The average of cosine is like 0.6 or something. And then you have QR over QR squared. Squared gives you Q to the 4. And the minus goes away because it's squared. So you end up with Broad's law IQ from the two. This term drops out. The average goes to 0. That goes to 1 or something, like 0.6. And you have Q over Q cubed. That gives you Q to 2. And then squared is 4. That's Broad's law. And if you put these in, you can use a lot of it. Right, so this function you can show is valid, Right, so it's a function for a sphere. You can also calculate it directly. Right, so you take that and then you're gonna do this, what we saw in the paper, like the form factor times the structure factor, and then the structure factor is this guy. So this is in fact where that idea came from, is like this kind of correlation. So you need the correlation function for the particles. Like what's the probability if one is in the particle of the other end of the arrow of direct distance r, also in the particle, right? So, that G of R means it's not the form factor for within the sphere. This is the function for if I'm in one particle, am I in the other particle? So 1, 2. It's a binary interaction between 1, 2 correlation function. So it's not as easy as doing for a structure. It's doing it for this crystal, right? So to get that, you need to do this business. Okay, so that's the correlation function you want to get. So this isn't exactly written. Actually, we can just go to Wikipedia on this thing. Let me just go there, because that thing I don't like. This is good. So here. All right, so that's that same equation. So this is the thing we want to get, right? Correlation between two of the beads, right? And this is the correlation between two of the beads if they were isolated. You just have a bead, and then a 1-2 correlation between those two beads as they float around in space, right? But then this is for when you have the beads packed together with a lot of other beads. So this thing's similar to the second viral coefficient, like the 1-2 things. And then this term is going to be correlating like the 1-3. So how if you put a third bead in, how does it impact the 1-2 interactions? And that's going to involve the total interaction between 1-2 in the presence of a 3. So that's H12, which is the thing that's going to give rise to the scattering, the crystal pattern. And then it's also going to involve the binary between 1-3. So basically it becomes an integral of all the possible 3s that you can find that would influence the 1-2. So that equation is called the Ornstein-Zernicke equation. He didn't win them.
One extra bead anywhere in space around.
All the other extra beads. So you have the one extra, but you could have all these other ones. So you're going to integrate over all those other extra beads. It's kind of in it. So it's a recursive formula because the thing you're trying to get is involved in the thing you're trying to get. Right, so it's recursive. So you need, in order to solve a recursive, you need another equation to do it. Right, so that's the idea. You need a what's it called? You need another function to say how to get the answer to that. Right, so there's a variety of, so that's Ornstein-Zernicke, and then there's a variety of closure relationships to get that. One's the Born-Green, which is the simplest. Then there's a Perkus-Yavik closure. So, and these all involve like super math. But one thing to say is that if you Fourier transform this thing, it becomes simpler because the integral disappears when you do a Fourier transform. So this would be the scattering function for the K would be Q. So it's the scattering function for the correlations, the S of Q. This is the binary one, and then this is how it shows up in a Fourier transform. So Fourier transform can like simplify your life sometimes. Right. So in the end, you can get an expression for that. It looks like this. If you use the Born-Green expression, this C becomes a form factor for the spheres. So you have that function, and this rho becomes a packing factor for how well the spheres are packed. If you use the Perkus-Yavik equation, this becomes a huge equation. It becomes like a complicated equation. So yeah, that's kind of that's kind of all I want to say about this, actually. So it's just, you'll see this in papers, Ornstein-Zernike, Perkus-Yevik, and then they'll be solving these, they'll be fitting curves like this to try to get the, so if you divide the scattering pattern by the sphere function, wherever, for the dilute one, then you can get just the S of Q plotted against Q, and it's going to look something like this. And you'll see, if you divide this by concentration, you'll see that this thing drops just like the other one dropped at low Q, and you get the chi parameter from that, just the same way. Like you're going to use the osmotic compressibility here, but this part has a peak in it, like multiple orders of reflection. But the single chi parameter decides the entire curve. So the peak and the breadth of the peak is decided by this intercept over here. Right. So it's kind of like it's a one parameter fit for this thing. If under the Ornstein-Zernike with something like a Born-Green approximation or Perkus-Yevik approximation for it, for resolving that redundant thing. Anyway, that's probably more than you need to know. You know, but basically, that's kind of it for the polymer stuff here. The next thing is to look at hydrodynamic radius. So do that next week, I think. You know, but anyway, so I'll probably, unfortunately, you'll have another homework with scattering. And it might involve some weird Perkus-Yevik thing or something. I'll try to dig something up. So anyway, so yeah, so we're doing that tour today, but I guess only 2 people are going. But if anyone else wants to, Candace is giving rides. But
I have room for 2 more.
maybe we can pick up a hitchhiker or something. You know, it's like, yeah. No, we're not going to your place. So we want to go to this extrusion factory right now. Yeah, instantly. In fact,
I would
You're-
like to go, but I have a class at like 1.
I think we'll be back by 1, you know?
We'll be back by 1.
Yeah, I mean, it's not gonna take long. All they do, all right, so they take copper, they push it through a thing and make a wire, and somehow they extrude polymer onto it and wind it up. It can't take more than half an hour.
Hopefully.
Yeah.
The last one was gonna be quick. but it was-
No, honest to God, this one is gonna be half an hour.
If they're like not like.
Yeah.
The last one was,